Works. All right. All right, we'll give this a whirl. We'll see if this works.
No, I put.
Are you guys cool with this, by the way? You're not. I'm not filming any of you, but you'll be picked up on the mic. Is that all right? We'll hear your voice if you want to talk. You can also not talk. Sean, you're the greatest. Thanks. What's up, Chris? Okay, we'll get you a cut too of the profits. So anyway.
Right.
So let's go through this. I want to make sure we have enough time to actually hit all 5 problems. So, how many of you, the first thing you did was just go through and decide. Friends. First thing you did was go through and decide which test was which. I think that makes a lot of sense. It makes a lot of sense. It's a way to not have to reinvent the wheel each time, or have to reinvent the wheel and then solve a problem each time. If you can kind of get an idea of which menus you have to go to and which data you have to process in which way, I think it makes a lot more sense. So let's go through that. The first one, the Chicago hospital worker. Lots of votes for Goffs. Tell me why that's a goodness of fit. Give me some reasons why that's a goodness of fit test. Steph, help me.
Because those numbers are not what they expected in percentages.
Good. You see the word observed, so you know you've got some observations. Perfect. And then Steph also noticed the expected distribution. So she saw observed, expected. That's a perfect setup for a goodness of fit. Awesome. Other clues.
We have an and, so we can turn it into proportions.
Good. We can turn them into proportions. I like that very much. Good. Other clues.
More than 2.
A big clue is you've got a chart with 4 headers on it. And you noticed as you went through, there was another one that had more than 4 headers. We'll get to that one in a second.
It's all
But
about expected.
say that again, Bobby.
It's all about expected.
Exactly. And notice the givens are in percentages, as somebody mentioned before. I think it was David. You've got 47%, 37%, 13%, and the rest, which is 3%. Thank you. So you've got 4 percentages, which then you can then apply. And we'll deal with that momentarily. We'll play with that one when we go back and review them all. So Goff, check. Love it. Attitudes toward obtaining an advanced college degree. I hear a vote for T-test, matched pair. Love it.
You could do T or a T7.
You could do either. Only one's correct, though. That's the problem with statistics. You can do anything you want. Now, let's talk about that, David. Let's also compare it to number 3 while we're doing that. Number 3 looks the same, doesn't it? But Amy's voting for 2-sample T-test on this one. I love it. So this is probably the most twitchy little difference. Leah, help me.
The first one has before and after in it.
One good-sized clue is before and after. Now, I was a little bit of a bastard here. On number 3, remember I gave you that partial clue that's not 100% correct all the time. If the sample sizes are different, it can't be a matched pair. Remember I said that earlier? If sample size. So what did I do? To test your knowledge of context, I made both sample sizes be exactly the same. That way you couldn't use that. You had to go strictly on context. One contextual point Leah just said is the before versus after. That's great. So you have to ask yourself, in these 2 problems, how many actual samples do you have? Look down at number 3 again momentarily. You've got 30 college students are broken into 2 groups of 15. Do those groups interact with each other?
No.
No, they don't. They're independent of each other. So you've got 15 of them that are checking a number of tasks, listening to music, and 15 that are not. Completely different, not interacting with each other. Those are independent. Look at number 2. How many groups do you actually have in number 2?
1.
You've only got 1 group, but it's measured twice, which makes it a single sample. It's the difference. And we'll get the mechanics of that momentarily when we actually sit down and do the problems.
That's the match pair.
That's the matched pair. So far we've got a goodness of fit number 1. We've got a matched pair in number 2, and 2 sample independent T in number 3. Are we good here? Yeah, good, exactly. An average test, a mean test. You got it, Kim. We good so far on the first 3?
Yeah.
Solid?
Oh, yeah.
Good. All right, let's go over to side B.
Why can't we do T-test on the 3rd one? It's before and after, isn't it?
It's not. You're not testing one group before and then one group after. You're testing one group over here and a second group over here.
Yeah.
Right.
2 groups.
What's that?
It said 30 people split into 2 groups. But they didn't.
Right, 2 different groups.
Yeah.
Not 30 people tested once and then again. Right? I totally get what you're saying, Mike. But that's what often happens is they get a whole bunch of people together and then split them into whatever number of groups they need, whether it's 2, 3, 4, 5. But they're independent groups. They don't interact with each other. Fair? Great questions. Great questions. Of course, I asked you earlier, none of you are going to be on camera. I've said every one of your names since we started recording. Is that okay? Okay, good.
Let's put in
Number 4.
93.
Hang on. We got here 2 prop Z. 2 prop. We got some agreement. Give me M. Help me out. Y. What's the giveaway? That's a good question.
So 2 different samples.
Oh, okay. This is clever. There are 2 different sample sizes. I like that. There are 2 different sample sizes. So how do you know it's not a 2-sample t-test, Ashley? Because you're looking for a percentage of success, not a number of successes. In number 3, you're looking for a number of successful tests. Here it's the percentage of success of a test. So it's a percentage versus an average. Very good, Ashley. That's the distinction. Once you've limited it down to 2 groups, you're either independent means or independent proportions, and then you have to ask yourself, what variable am I testing? Oh, percentage of success. Other things you can look for is out of. Notice how it said 71 out of 110, 93 out of 120. Textbook proportions right there. Just setting up as a fraction, x over n. Cool? Awesome. That leaves number 5, that has to be the only thing that's left. It's got to be the Anova test. So the reason, now again, you did it by process of elimination, which is perfect. But what are some other giveaways?
3 columns.
There's 3 columns. How can it not be Goff? Because you're testing averages. Are their averages different? Not are their proportions different. Are the averages different? Plus, you also have long lists of values as opposed to one observation in each list. That's the way a Goff is set up. You've got one category, an observation. Another category, an observation. Another category, an observation. You've got numerous variables in each of the columns, which is another good giveaway. So I'm trying. I mean, yes, I want you to, when you get the exams on Monday, to sit down with them and do this. Kind of sit down with all 5 of these and figure out which one is which. But at the same time, I want you to be able to do them independent of each other as well. For example, we started at number 1 and went to number 5. I'd also like you to have success if you started at number 5 and went back to number 1. So if you saw Anova first, you know it was Anova. Does that make sense? Good.
Yes.
But it sounds like you guys have. I heard the discussions as I was walking around, which is great. The only things I really noticed that were going on as far as what were tripping people up were TI inputs. You were getting domain errors. You were getting graphical errors. Easy fixes. If that happens on Monday, just come see me and let's fix it then. Let's not get you hung up on that on Monday. Yeah, David, please.
So we were supposed to run just a straight t-test on 2?
On 2, yes, sir. Because there's only. We'll do that. We'll go in order now. Let's knock them all out. Right? You're going to keep them. And then I'll post this, and hopefully this is useful. I'll post this later on. I'll put it up on YouTube. I'll link the audio into it. And what's that? Did I make the boxes with the mic came in? Cool. So it's a Yeti microphone. I love that. A Yeti. Cool. Let's play. Chicago hospital worker. We agreed it's a Goff. Okay. So we've got this observed list. I'm going to go ahead and start this off with hypotheses. Although I'm not going to ask you to list the hypotheses on the exam, you can feel free to list them if you want to. That's totally fine. And I like for the review portion to actually have these listed. I think it makes sense to see them. So what you're looking at is you're looking to see if in the null the proportions are as expected. And the proportions as expected is the chance of a type O is 47%. The chance of a type A is 37%. The chance of a type B is 13. And you guys said the AB is everybody else? 3%? Is that what you guys said?
Yeah.
Good. Perfect. Have to sum to 100. Just out of curiosity, how many type O's do we have in here? Do you guys know your blood types? I'm type O. Type A's? Type A's?
A negative.
Okay. I guess that counts as A negative. B? Type B's?
Negative about it.
Any ABs?
That's it?
Interesting. Now
That's
that's cool.
1A.
Does anybody not know their blood type? That's a good size chunk. Of the ones that voted, but of the ones that voted, you roughly followed this. That's kind of cool. Roughly followed that, which is pretty rad.
There wasn't 13% Bs.
I said roughly, right? I mean, with that small a sample, you have to accept so much variation. Does that make sense?
Yeah.
Good.
Yep.
What's the opposite? What's the opposite of that? Good. There's a couple ways you could say it. The way I was saying it in class was at least one is off. At least 1% is off of expected. Another way of saying it is they're not all what they should be. There's many different ways of saying it. But the big idea is you're running the test to see if at least one or more of those is significantly different. That's why I said, Joe, there weren't that many people voting, so therefore I understand there's not 13%, but that would have such a huge plus or minus on it that basically we can say we can't prove it's not 13%. Cool? Ashley, go ahead.
Instead of doing that, I just kind of reversed what the question said, and the question is the data sufficient enough to show a significant deviation? I put either it does appear to have a significant deviation or it doesn't.
Totally fine.
Okay.
That's why I said there's many different ways to say it verbally. But basically what you're looking for is this or something else. But I love that. That or a deviation from that. Awesome. Totally awesome. Cool? All right. So what we have to do is we have to set up some lists. And basically, the only list you have to set up is the expected list. You've already got the observed list, right? You've already got, let me get my data sheet. You've already got your observed list, which is over here. And we'll just go right down. Type O, type A, type B, and type AB. Okay. That's what you saw. That's what you saw in the Chicago hospital. What should you have seen, assuming that these percentages as given are perfectly accurate? And I say perfectly, meaning not significantly different. What did you have to do first, friends? Very nice. You have to figure out how many observations. Compare this to the M&M experiment in class on Wednesday of last week. The first thing you guys did was crack open all the bags and figure out how many colors that you had. Then we had to figure out how many colors we should have had. But in order to do that, you had to know how many total pieces of M&Ms that we had out in the room. Good. So you sum these bad boys up.
187.
187? Thank you. And that's good. That's your N, if you will, your sample size. And then you have to apply the percentages to that 187 to figure out what you're going to get here, 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 and here. Go ahead, Chris.
We just have slightly different things if we did them in the column or we did them first and got a whole number.
Say when you say first.
The E number.
Yes.
Like if you did them in the column, like 0.347 times 187 in the column.
Oh, in the TI.
Yeah.
I think that's a great idea.
That's the way I do it.
I think let's do it that way. I think that's the easiest way because it's one less step for you guys to have to do. Now you're saying slightly different because of rounding.
Right.
That's the difference, is because those are going to be basically most likely longer decimals that you're going to truncate when you're writing them down. Let's let the TI deal with it. Okay. That's why I have computers to deal with computations.
Would either way be wrong?
I promise to find you data sets. I was telling these guys in the back, I promise to find you data sets where their p-values are far enough away from 5% either way so that rounding won't be an issue. Does that make sense? Yeah, I promise. I promise that rounding won't be the downfall of someone. Cool. But I like your idea of doing it in the TI. So I'm going to go ahead, turn this bad boy on. I don't know what this is, so I'm going to clear it out. Oh, that's L4 and L5 anyway. Just go over here. Oh, this brings up a good point too. Michaela, thank you for bringing this up. As you guys are using more and more data inputs in your TI, you might be using, like I had all 6 lists used here at one point. Keep track of where your data is. It's really easy to put your data in a list, whatever list is there, and then run a test on another list inadvertently. And you're getting goofy answers, but you might not know that they're goofy because you ran what you thought was the correct test. So just try to keep track of where everything is. All right, so observed, 73, 77, 29, 8, and then we just go down here and apply the percentages. 47% of 187. So this is what Chris is saying to do. I think it's a great idea. Just press enter. That's what it's going to be. Now notice, you get the truncation here, or excuse me, you don't get the truncation here, but some of you might be calling that 88. I mean, understandable. Don't be alarmed by 87.89. Some people tell, you can't have 87.89 people. I say, yes, you can't. But you can have them on average. You can average 87.89 people. So in other words, if 47% of your blood types are O, out of every 187, you're going to average that many type O's. You can average a decimal. It's totally fine. Remember, 1990 census. How many children per family? 2.5. Totally fine. Totally fine. 37% of 187. 13% of, and 3% of. There we go.
So right now, Sean, I want to
Sir.
ask one real quick question.
Go.
If I was testing for assumptions, right there I would know, right?
You would know what?
I would know if I could run the post.
Awesome. Adam, this is great. And again, over and above Monday's exam, just so you know before I answer
It
this.
is on there.
It's over and above the in-class exam. The in-class exam. I asked you to test for assumptions sometimes on the out-of-class stuff I do. I don't want you getting bogged down with that on the in-class stuff where you're freaked out anyway. Right now, you should have at least 5 in any of these categories. That means your sample size, as Jolene mentioned before, is large enough. So as long as you've got at least 5, that means you've captured enough of your population to see whatever behavior is happening. So good. Very nice, Adam. That's right. So if you're testing this thing like out in the world, you'll know you have enough data if those are all at least 5. Go, Kaylee.
Should I do this wrong? Because in my L1, I put the percentages, like the H0 percentages.
These guys here?
And then in L2, I put the percent of the observed, like out of the total. Like
The problem only exists in the way the test statistic is calculated. Remember when you calculate it, you square the difference? The problem is that squaring is going to distort the percentages. If it wasn't squared, it wouldn't matter. You're going to have slightly different results. You are. Because you want to go by raw data values. Is that fair?
Yeah. I did that.
Maybe not. It's totally easy. It's easy to do, and that's one of the confusing things about the GOF is you have to remember you're actually analyzing counts versus the percentages themselves.
So the 87.9 is what you should get
If
47% of 187.
yes, ma'am. That's perfect. Kenny, go.
So if in L2 your data is less than 5%,
Less than 5.
Less than 5, you couldn't do the test.
You shouldn't do the test. Exactly. You should not. That's exactly correct. You shouldn't run the GOF if that's less than 5. You failed to meet the assumptions, basically, of the test. But again, I'll find you a good data set to behave. I promise. I promise. But it's a great realistic question. Like you'll see on your take-home exam. I think it's the second question. Where I have you run a t-test, find some powers, and then go, oh, by the way, why shouldn't you have done any of that? Because that they don't meet the assumptions of the tests. So therefore, you should do something else. Sorry, Lindsay. I just pissed you off. She's glaring at me. She's like, you SOB. But that's the thing. You should start, not on Monday. On Monday, I will give you well-behaved data sets, I promise. But in reality, I promise. I promise. I'll give them well-behaved data set. I do. I promise. But in reality, data sets are rarely well-behaved. You have to deal with them on their own terms. I mean, in reality. So it's a good question. Let's do it. Let's do it. So this is the only one that's under program, right?
Yes.
Program, GOF.
Go.
Well, I'm trying. And then just tell it where your data is. Your observes are in L1. Your expecteds are in L2. Let it run its thing. Your test statistic, it's about 5. It's about 5. Your p-value is 15. Who do you believe? Who do you believe? Are the percentages basically what they should be, or is something off? They're basically what they should be. You haven't deviated enough from what they should be to think that one of them's skewing the results. Perfect. They haven't deviated enough to think that something's skewing the results. So, would you have to run a post hoc?
No.
You wouldn't have to.
No.
The only reason you'd think about running a post hoc is if that was very small, which would imply something was off.
Right.
You're suggesting, or the p-value is suggesting, that nothing is off. Everything is basically, there's no reason to think anything is off. Ricky, go.
Is it important to put when on the test, p equals 0.14?
You mean I want this. I definitely want that. I don't care so much about the variable p, because it's p for all of them. I care about this one because I need to know that you guys know which test you're running. And that's just a guarantee. That's why I left that in there, right there. So yeah, tell me chi-square equals 5.3 or 5 or 5.33, whatever.
Okay.
And then tell me, you can put p equals 15% or just 15%. But I do want the variable for the tests. So you're going to have a chi-square, an f, a z, and 2 t's. And we'll see each of those today as we play.
Oh, lovely.
Is that fair?
Mm-hmm.
Cool with Goff? Questions, please. Please, go, Hannah.
Are you wanting the p-value changed to a percentage?
If you want to. Doesn't matter to me at all. Doesn't matter to me at all. Call it greater than 5% if you want to. That's also. Some of you have been doing that on your assessments. Rather than giving me the p-value, you've been just saying it's bigger than 5%. Totally down with that. That's what you're looking for, right? You're looking to see that it's greater or less than 5%. That's our arbitrary, pseudo-arbitrary cutoff. Leah, was that your... Oh,
Then it's okay to just round it to 0 then. If it's
that?
0.0, no, not.
Oh, like a small one.
Yeah.
Yes. If it's like 0.0003, call it 0. That's fine. Go ahead, yeah.
When I did homework.
Yes.
Instead of transferring everything into whole numbers, I did them all into percentages.
These? Those aren't percentages. These are.
Well, when we were entering.
Oh, gotcha. Right.
Now, why? It seems like the proportions would be the same.
No, the proportions are the same. It's what the test is testing. It's testing counts, not percentages. And that wouldn't be an issue. It wouldn't be an issue except for the fact that the statistic is squared, which distorts that difference. That wouldn't make a difference otherwise. So that's why you have to go with counts. You have to go with counts. Exactly. Oh, yeah. And I have no good answer other than the distribution is set up not to behave that way. That's
You have an N there.
you do. You have to use the n. Right. So basically, for each of these categories, you have to take that n.
Yeah, I mean, we got to make them both.
You got to take the n and multiply it by whatever the p is. This is p of type O, p of type A, p of type B, and p of type AB.
What we did was we took the n and over we found out what the observed was
Over the n, basically, and got the percent. Exactly. Totally. But the test is not set up to test percentages. It's set up to test counts. And it's a function of how it's set up. I mean, there's nothing wrong with your logic. It's perfectly fine, because essentially you're doing the same thing, but you're not testing the same thing because of the way the chi-square distribution is set up. Not a very satisfying answer, I know.
It just seems like with the word proportion. That's what
Of course, but you're using the proportion at every step. You're using it at every step. It's just being included by the fact that it's a count. So, like when the 2-prop z test that we're doing later, you actually see the x's and the n's and they become proportions. You're actually testing, if you will, just the x's here, and the n's are kind of in the background. Right. Instead of x over n equals p, it's p times n equals x. It's just the way it's convoluted. Cool? This is why I love today. We can do this today and talk about it and get everything squared away. Let's continue, because I want to make sure we're running out of time, even though it's almost 9 o'clock. Anyway. I mean 10 o'clock, yeah. But the clock says we have an hour and a half. No, I'm kidding. Bad jokes. Let's do the next one. Number 2. We've agreed this is a t-test. We've agreed it's one single sample. Love it. Let's clear some space. All right. Let's get some nulls and researches. So it's a single average. Single average. And I think the way I was doing these before, I was calling this mu with a sub d. That's just reference because we're looking for a difference. Because that's what you are looking for. To see if there is a difference between the before and after scores for each student. You're not testing all of the before scores versus all of the after scores. You're testing each student's difference between their before and after. It's a subtle difference, but it's a big difference overall in the theme of what you're testing. So, let me ask a question. You guys, I'm assuming, put the befores in L1 and put the afters in L2. Let me get caught up with you guys then. Let me get caught up.
Why are you writing mu d instead of just like mu1 is not equal to?
You can do that too. I was using D as a subscript earlier, so I'm just sticking with that. Let me get caught up here, friends. 11, 8, 10, 9, 6, 13, 11, 12. 6. Okay, and Okay, beautiful. Let me ask a question. You found the difference. How many did L1 minus L2? Just straight across. How many did L2 minus L1? Just about split halfway. Does it matter? No. If you do L1 minus L2, so let's put here. What's this going to be right here in the null? Equals to 0, because you're assuming there is no difference. So mu d is going to, I'm going to make this a piecewise function, that's okay. It's going to be either less than 0 or greater than 0, depending on how you put what you put in L3. So if it's going to be less than 0 for those of you that did L1 minus L2. Why? Explain why it will be less than 0 in that case. Chelsea, help me.
Isn't it because they're all negative?
You'll be expecting negative values. Yes, my friend. If you're expecting higher scores on the after portion, you'd be expecting smaller minus larger, which results in negative or less than 0 values.
U2 is larger than.
Exactly. Which would be reversed if you did L2 minus L1. It'll be reversed. So in other words, you get the exact same p-value, but your test statistics will be opposites, as Bobby noticed earlier, of each other. I'll do L1 minus L2. Doesn't matter. It doesn't. There's our differences. Or they're positive, where the negative, they'd also be opposites if you did it the other way. No big deal. Just keep track of which one you did. That's the important thing, is making sure you put the correct sign in your test. Otherwise, you'll get the complement of the p-value that you need. Cool? Let's do this. T-test, love it. Love it. We have data. The mu we're testing against is 0, because we're assuming there is no difference. Our data is in L3 with a frequency of just 1. You got each student accounted for one time. And this is where you got to be careful. Make sure you grab the correct sign. All right? Shall we? We shall. Let's see how these kids are doing. All right. I can tell right away it's working. Because it was a left-tailed test for me. So if I was going to see area, if I was going to see a large p-value, I would have seen it over here. But I didn't. And this echoes it. So Catherine, here's your 0. If you want to call it 0. Was it Lee or Catherine that asked me that question about rounding to 0? Good. I'd call that 0. Test statistic, you're 4.2 standard deviations down from average. That's pretty far away. Which it looks like. Give me the conclusion. There looks like there's improvement from the before to the after. Whatever intervention happened, looks like there was some significant improvement on that.
Just do a two-tail with this.
You could also do a two-tail, just look for a difference.
Would I be right on the test?
But I asked you to see if there was improvement. That's the difference, no pun intended. The difference is, what am I, sorry, terrible math jokes. I'm asking you to test. Now, I think in number 3, I did ask you for just a difference, for two-tail. Yeah, so just read the context to know if it's left, right, or two-tailed. Just look for, if I'm asking for improvement, for a decrease, that kind of a thing. Fair enough? Good questions. Those of you that ran it L2 minus L1, what would your p-value be?
Same.
Exactly the same. What would your test statistic be? Positive 4.2. Exactly. Because you'd be over on that side. Exactly the same. But the sign is crucial, because if you put the sign in wrong, you're going to get a humongous p-value, which implies that there is no difference. But just looking at the list itself, you can tell there is. At least in the first few, assuming that that's a random smattering of the entire set of 25. Cool? Ish? All right. Adam, go.
I was just going to say, somebody said a minute ago, so as a trick, just to double check yourself, if you've got a lot of negative values,
Yes?
the less than sign looks like what you're going.
Well, careful. That's begging the answer. Now, that's a great point. But you're assuming there's going to be a small p-value by doing that.
Right.
Now, the reason that can backfire, and I don't expect you to remember this at all, because it's about week 3 or week 4 of the class. We disproved the Florida Sun's newspaper article. The whole Jeb Bush repeals the helmet law in Florida. Oh my God, the number of deaths are way up. But what we actually proved, statistically supported anyway, was that the percentage of death was way down. So we were expecting one thing, and it was actually exactly the opposite. So be careful. You don't want to beg the answer in your result. Great point. But it only works if you're expecting and going to get a small p-value. Fair? Great point. Great point. Let's do number 3. Okay. I can't wait to hear what this sounds like.
Hey, Sean,
Actually, I can.
I don't want to hold this up
Go ahead.
all the way through.
No, go ahead.
I'm just curious why running a 2-sample T got so close to the same answer.
I'm not saying it can't. I'm saying it's testing the wrong thing. What you're looking at, I love the, David's point is when I run a 2-sample t-test, I get almost the exact same result. I'm not saying you won't. I'm saying you're testing the wrong variable. When you do a 2-sample t, what you're doing is you're looping all of the before, and you're averaging all the before scores, and then all of the after scores, and seeing if there's a difference there. But that's not what you want. You want to see if there's a change in each student from before to after. So I'm not saying you can't get numerically the correct answer.
No, we even pitched it as a match compare, and then we just, for some reason...
It's okay. That's why I like this day, so we can sit down and actually chit-chat about everything we've been talking about for 5 weeks.
I was just curious why it actually came out that close. It seemed like it would be...
And it can, or it can be extraordinarily far off. It's just you're testing the wrong variable. And that's the beauty of the analysis, is that the statistical test won't tell you if you're right or wrong, unless you've got a data entry error. It'll just run the numbers for you.
Okay.
So, great question. Not a hold up at all. Not a hold up at all. All right, let's look at the actual 2-sample t-test, which is number 3. Let me get these data in here. We got 26, 19. And we got, oops, that was dumb. If I have time when I edit this down, I'll chop off all my stupid data entry. All right. We're trying to see if kids that use music and kids that don't use music, what? Good. Score different numbers of tasks correct. Score different. I'm just looking for a difference here. Just looking for a difference. So, the average number that listen to music versus the average number that don't listen to music, assuming the music is not doing anything,
Those are equal.
they're going to be equal. There's not going to be any difference in the tasks completed. But assuming the music is doing something, or is doing something either good or bad, we're going to look for a does not equal sign. And again, everybody's going to have the same signs on this one. There's not going to be any difference. Because, well, actually, literally, there is a difference. They're not going to have a less than versus greater than, because you're just looking for a pure two-tailed difference. Cool? Make sense? Good. Let's run it. And this, again, David, I loved your question earlier about the matched pair versus the two. You have two groups each being measured once versus one group being measured twice. That really is the biggest difference. Eric, please.
All right, so the difference is between before and after, and then for the 2-sample is the test is experimental and the control group.
Perfect. If you can break it down to an experimental and a control group, very helpful. In this case, the control group would be who? You got it. The no music group, essentially. You're trying to see if music's doing something. So you're going to keep both groups essentially the same, except one gets to listen to music and one doesn't. That's fantastic. Look for the control group idea. It doesn't always work that way, but that if you do see a control group, you know where you are. Kaylee?
And this one, group B, is actually the control group.
No, is that the music group?
That's the non-music group.
Oh, that's the non-music
It says
group.
in the first group they listen to music, in the second group they do not.
Well, sure. So the non-music group is the control group. That's what I'm saying.
It'd be-
Did I say it backwards?
Yeah.
Oh, I'm sorry. But yeah, that's exactly correct. But you don't have to always have a control group. It might be that you're testing versus a certain kind of music and a certain other kind of music. But usually those are tested via Anova. So you also have a third group with no music to see if there's also that interplay. But the control group is a great idea. Fantastic idea. All right. We've got data. So make sure you put your lists in. I got L1, L2. Frequencies, friends? 1. They're just ones. You're counting them each one time. Remember the alpha problem. When every time you jump into a list, it sets in an alpha mode. Just make sure you turn that off as you go. We're testing for a not equal. We're not pulling. And we're ready to go. Here we go. There's 0. There's 0. Here's a 95% confidence interval around 0. Looks like what?
Big P.
Big P, like that. There's your, we're 1.5 standard deviations, which is within the 2, roughly 2, for a 95% confidence interval, which means there doesn't appear to be a difference. We're close enough. We're close enough. It's positive. It's positive, which means the music kids did do better than the non-music kids, but not...
Significant.
Oh, listen to that music to my ears. Not statistically significantly. More music to my ears. Stereo. Sorry.
Well, we only have to, like.
We do, and we're going to get there. I just want to make sure we cracking the whip, Michaela. Cool?
Yeah.
Awesome. Flip it over. All right. Now, we're trying to see, is task B easier than task A? All right, what are we going to assume? We're going to assume that it's the same. So the proportion that are getting task B right is the same as the proportion that are getting A right. There's no reason to think they're any different until we actually test and look. But we'll see if task B actually is getting correctly, getting done correctly at a higher percentage than task A. Cool? Make sense? Does everybody see that logic of how you're setting this up? That's why originally I didn't have that little parenthetical bit in there. That is the percentage. But I realized that can be somewhat confusing. Because if something's easier, I didn't realize this, it was giving a psychological less than sign, easier. So, but if it's easier, you're getting it done more correctly more often. So that's why, okay, good. So we're happy with this? Let's run it.
Thank you for parenthetically.
Well, good. I think it makes sense. Again, as I try to assess, as I look at things, and it's throwing people off for non-statistical reasons, that doesn't make any sense not to change. Beautiful? Good. You could run this as a goth, but it's overkill. X1, N1, this is a good one. We were getting domain errors on this one earlier. Yeah. Some people were getting domain. Make sure that X is the number of successes and N is the number of trials. If you reverse them, the TI gets upset. So we'll go, I'll put B in 1. So B is 93 out of 120. Fair enough?
Yes.
And then 2 is 71 out of 110. Yeah, this is what I can just do greater than. This is what I can do greater than. Could you reverse them and go less than?
Yes, you could.
Absolutely. How would your p-value differ? Trick question.
Not at all.
It wouldn't. How would your test statistic differ? It'd be the opposite. It'd be the opposite, right? And that's totally fine. Doesn't matter to me. Doesn't matter to me. Ready? Let's draw it. It draws much more quickly. Okay, a little bit of area, but not much. We're outside of that 1.645 for a one tail. We're outside of 1.8. So about 2.2 standard deviations up. 1.5% p-value. Not even better than a difference. B's easier than A. Right. B's easier than A. B's easier than A.
Let's do test B.
What's that?
Let's do test B then.
Thank you. I'm here all week. Very nice. Very nice. Feeling better. I say that's good. Just married. Waiters and waitresses. Cool? Fair? Awesome. One last test drawing and keep Michaela happy. We got to run the Anova. We're going to see if there's a difference. Let's set the variables up. We're looking at the PERs, PER ratios, or PERs, excuse me. We got. Oh, you guys are good. We're looking at financial versus food versus leisure goods. That's a G. What's the opposite?
They do not.
They're not all equal. Good. At least one is different. Right. At least one is different. They're not all equal. I love how both of that sounds. At least one is different. They're not all equal. That all sounds good to me. So all you got to do is run the data. And this was that ridiculous computation that I would never, ever make you do manually. So let me just get myself caught up here. Grab 3 lists. 8.83. Yeah, I'll try to, when I get back to the office and actually start processing this video, I'll try to cut some of this crap out.
So we can curse and do all kinds of.
Oh, yeah.
Wouldn't you want the data entry in there so they know what your data is?
That's a good point, Michael.
I'd leave it.
That's a good point.
It even shows up on the screen.
Well, I checked that. It's actually half the window, so I'm hoping it will. It's actually half of what you're seeing. That the fisheye is definitely ridiculously large. Oh, is this still recording?
Yep.
I think the battery's almost dead, though, so let me hurry up. That little view screen, I should have pulled that off. That drains the battery. And I did bring the plug, but if I just shut up and keep working.
Sean, you keep going.
Oh, crap! If I just shut up and keep working. Crap! 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 Gotta get kicked off of YouTube. Cool? Oh! Hang on a second, I'm nervous now. Let me plug this thing back in. Just gonna plug this in.
Boom. Still going.
Okay, here we go. We're almost done. Stat, test, Anova at the bottom. Run the lists. With commas. With commas. What's going on? There's a lot on here. That's what we're looking at. There's your F, your test statistic. What does this tell us?
Something's different.
One of those averages is different. On Monday, what do you do next? Nothing, you stop. On Monday, you stop. I have you do a post-tops on your out of class. I have you do a post-top. Or on your quiz if you chose to do the quiz today. But on Monday, you stop. You say, at least one of them is different. And I've had fun in this class, and that's it. Maybe you haven't. That's okay, too. Just, I'm done. At least one's different. Cool? Makes sense? Okay, awesome. So, we'll do, yeah, that'll be Monday. We're at 8 o'clock here Monday, yes? Yeah, I think that's it. I haven't written your exam yet, so I'll write it and then I'll touch base with you guys again to let you know if anything changes. I'm going to keep it in this format. I like this format. It's pretty simple, straightforward. But that's it. Cool? There we go. Rock and roll, my friends. Have a good weekend. We'll talk to you on Monday. I have office hours posted for exam week, a little bit different. Rick Millie in the mail. I'll catch you someday. No, I won't. I might get, I'm only getting older and slower. What's happening? I guess I should stop recording. Thank you, good night. We love you all!
Maybe staff for a raise.
I had to get my Aussie on. I had to get my Aussie on.